Well, welcome back, class. In the last lecture, we talked about Avogadro's number. We talked about Dalton's atomic theory. We talked about the experiments that led to our basic understanding of the fundamental structure of an atom, including the elementary particles of proton, neutron, and electron. In this lecture, we're going to talk more about isotopes, average atomic mass of elements, and then close with a brief discussion of ions. Let's begin with isotopes. When I think of isotopes, somehow, crazy me, what pops into my head is Isotope Feeney. What? Isotope Feeney was sort of a funny bad guy in a cartoon called Tom Terrific. Tom Terrific is shown on the left. He's the one with the funnel thinking cap. And his friend, Mighty Manfred, the Wonder Dog. And Tom Terrific solved all kinds of problems. And one of the baddies, mean guys, was Isotope Feeney. And this is one of the first cartoons I can remember from the Captain Kangaroo show around 1960. And I guess this scarred me for life because the first scientist that I guess I was familiar with was a bad guy, Isotope Feeney. I guess I haven't gotten over it yet. Okay, what are isotopes? Let's think about an element, magnesium. We can describe magnesium with a symbol Mg as shown, and we usually give a couple of numbers. One is called Z, the atomic number. The atomic number for magnesium is 12. That means it has 12 protons. That is, if you are an atom with 12 protons, you are magnesium. We also can describe it with a mass number, what is called A, the mass number. And this mass number can be 24, in which case magnesium will have 12 protons and 12 neutrons, because the sum of protons and neutrons is the mass number. So this is a simple way that we represent magnesium. Now sometimes putting the 12 is redundant with the Mg symbol, because if we say Mg, there must be 12 protons. But for sake of clarity, we oftentimes write the 12 as well. So, okay, then why does the periodic table, which I know you've looked at now from the last lecture, why does the periodic table have entries such as the ones shown? Under magnesium, if you look at the periodic table, you'll have 12 for the number of protons. Sometimes we put the 12 at the top and sometimes at the bottom. Don't let that bother you. But my point is, why do we have 24.305 by magnesium? And likewise for chlorine. Chlorine has 17 protons. But why do we have the mass number of 35.453? My point is, why is this not a whole number? Why is it something in between? Well, that's because there exist isotopes. Now, there are a couple of reasons, but one reason is because there exist isotopes. And most elements have isotopic forms. An isotope and the phenomena of natural radioactivity, which is related in many cases, were discovered from the findings of Henri Becquerel, Marie and Pierre Curie, and Ernest Rutherford, that we'll discuss radioactivity and nuclear chemistry or nuclear physics later, probably in the second semester. But before that, we need to know the basic concepts of isotopes. An isotope is a form of an element having a different number of neutrons in the nucleus. That's basically it. For example, boron, B for boron, exists as two isotopic forms, boron 10 and boron 11. Again, the 5 means it's boron because it has 5 protons. But obviously boron 10 will have 5 protons and 5 neutrons. Boron 11 will have 5 protons and 6 neutrons. In the periodic table, if you look at the periodic table for boron, you will find a value of 10.811 AM units by the symbol for boron. Now, turns out this 10.811, as you probably imagine now, is an average atomic mass is due to the fact that 19.91%, nearly 20% of the boron atoms are the boron-10 isotopes, and a little over 80% are the boron-11 isotope. That boron exists in that proportion, 20% of one, 80% of the other, in nature. And that the average is a little closer to the heavier one, so that the average is 10.811. That is the most important reason why the numbers in a periodic table oftentimes are not whole numbers. Now further, the exact mass of boron-10 is not exactly 10. It's 10.0129 AMU units. And the exact mass of boron-11 is 11.0093 AM units, as is, they're not exactly 10 and 9. Now, we'll discuss this later as to why the mass of particular isotopes is not a whole integer number. That has to do with something called binding energy, which we'll get to later on. And in a minute, we'll discuss how we can actually measure, experimentally measure these exact AMU values for particular isotopes. But again, consider this table for boron-10 and boron-11. Both have 5 protons. One has 5 neutrons, one 6. The actual mass in AMU units determined experimentally, as we will discuss in a minute, is 10.0129 for one, 11.0093 for the other, and I give you the percent abundance, which I just mentioned a second ago. So to calculate the average AMU for boron, the average AMU is this sigma is the sum of the fraction or the percent abundance. That's what F is standing for, the percent abundance or the fractional abundance actually. The fractional abundance times the mass of each isotope. So if there are only 2 isotopes, which is the simplest case, the fraction of isotope A, the first isotope, times the mass in AMU units of the first isotope plus the fraction of the second isotope times the mass in AMU units of the second isotope. So for boron, the average AMU is simply 0.1991 times 10.0129 plus 0.8009 times 11.093, giving you the value that we have in the periodic table, the average atomic mass of boron being 10.811 AMU units. Now try the following on your own. Chlorine has 2 principal isotopes. One's chlorine 35, for which the natural abundance is 75.78%, and the exact mass of that isotope is 34.9689. Now you'll notice this is close to 35, but it's not exactly 35. And the second isotope of chlorine, chlorine 37, exists as 24.22% of the natural abundance of chlorine, with an exact mass of 36.9659. Again, close to 37, but not exactly. So calculate the average atomic mass of chlorine given the fact that it exists as these 2 isotopes. You can pause and solve the problem and turn the video back on again. Were you able to solve it? Well, let me point out that this type of problem is really fairly easy, and I hate to tell you, but it's so easy that it's not one I can hardly test you over. It's just taking the average of 2 numbers. Most likely, I would give you the average atomic mass of an element and give you the exact masses of the individual isotopes and ask you to calculate the percent abundance of each. Now, this really isn't a very difficult problem, but you have to realize the trick. That is, you have another equation that you can call upon to make it a 2-equation, 2 unknown problem. That is, this type of problem is solvable if there are only 2 isotopes and that the fractional abundance adds to 1, so that you can call upon the second equation, setting up a simultaneous equation situation, of 1 equals the fraction of the first plus the fraction of the second. We'll go over these in some problems, I'm sure. Now, there are many other important isotopes, and let me just point out one other one that you've probably heard about. Hydrogen exists as 3 isotopes. The most common isotope of hydrogen hydrogen 1 is what we call protium. It simply has a single proton in the nucleus. That's it, a single proton in the nucleus plus an electron in its orbit. There also exists an isotope called hydrogen 2, which we give the common name deuterium. It has one proton and one neutron in the nucleus, plus an electron in the electron cloud. And also we have hydrogen 3 called tritium, which has two neutrons and one proton, plus an electron in the electron cloud. Again, notice that to be hydrogen, you have one proton, but you can have 0, 1, or 2 neutrons. Now, the connection with radioactivity is that in some cases, the nucleus of one of these isotopes is not stable. In the case of tritium, its nucleus is not stable, not as stable as that for deuterium or protium. So the tritium will undergo a very slow nuclear decay reaction. We'll talk about that later on. Other elements that you've probably heard about, carbon-14. Carbon-14, 6 protons, 8 neutrons, is not stable and will undergo a very slow nuclear decay reaction. And of course, there are many other isotopes that undergo nuclear decay reactions leading to natural radioactivity: uranium, radium, thorium, technetium, cesium, lots of examples of elements that will undergo some type of nuclear decay reaction. Again, later. So we said that we can measure the actual AMU units, the actual mass in AMU units of isotopes very precisely. This is done using something called a mass spectrometer, a method of determining the relative mass of isotopes. In this kind of experiment, the path of a charged atomic particles is bent by a magnetic field, and where they strike a detector can provide the mass to charge ratio. Let me give you an example. Shown in the slide is a pattern for chlorine. Chlorine will travel through a mass spectrometer and show up as two peaks. One chlorine 35, one chlorine 37, back to what we said in the previous slide. And the relative heights of the peaks can actually be used to determine the percent abundance of chlorine. So this is just an example of how some of this information is experimentally determined. Because chlorine has 17 protons, that's to be chlorine, you have 17 protons. Chlorine 35 has 18 neutrons. Chlorine 37 has 20 neutrons. You might be curious as to why there is not a peak for like chlorine 36, which would have 19 neutrons. Turns out there's a reason for this, and again, you have to wait till we cover the chapter on nuclear chemistry. Just to give you a hint or a preview, nuclei that have both an odd number of protons and neutrons are not very stable. They're disfavored in nature as compared to nuclei that have an even number of each or an even odd combination. Interesting. Going back again to our basic definition of an AMU unit, a decision was made around 1960 or so to establish the most abundant isotope of carbon, carbon-12, the one with 6 protons and 6 neutrons, to have a relative mass of exactly 12 AMU units. This resulted in the definition of an AMU as being exactly 1/12 of the mass in AMU units of carbon-12. What is called the unified atomic mass unit, what we've been calling an AMU unit, can be given as a symbol U or DA for Dalton, John Dalton. It is now defined as exactly equal to 1.66053940 times 10 to the minus 24 grams. This is the value, this is the mass in grams of an AMU unit. And again, if you happen to plug that number in your calculator and take the inverse, you will get Avogadro's number. That is, it takes Avogadro's number of something with this mass to yield 1 gram. Remember our 1 gram M&M. Just as some asides, I had show you in a paragraph that for many years physicists and chemists had slightly different definitions of an AMU, but in 1961 they decided to come up with an agreement to base the definition on carbon-12, that particular isotope of carbon. Another thing just to have you think about. We had in the tables earlier that a proton and a neutron have masses of slightly more than 1 AMU unit each, 1.00727 for a proton, 1.00866 for a neutron. So you have to think, if we have 6 protons, which have a mass of slightly more than 1, and 6 neutrons, which have a mass of slightly more than 1, how can that add up to be exactly equal to 12? Shouldn't it add up to be slightly greater than 12? And the answer is yes. And again, we'll have to cover this later in a chapter on nuclear chemistry or nuclear physics. Turns out it's something called a mass deficit. It's related to binding energy, and I say in this slide, think Einstein. Finally, in this chapter, we want to talk about ions. We want to define what an ion is. A neutral atom will have the same number of electrons as protons, so that it will be neutral. But if an atom, such as sodium, loses an electron, a process that we call ionizing, it will form a positive ion, what we call an ion, a cation in this case, sodium plus 1. It will have a net charge, in this case plus 1, because it's lost an electron, it has more protons than electrons. If an atom such as fluorine gains an electron, somehow gains an electron, it will form a negative ion, what we call an anion, fluorine minus 1. And we'll see that cations and anions have totally different physical and chemical properties from their parent atoms. Do not confuse ions from their parent atoms, and do not drop charges. It's a major sin to drop charges. That is, sodium Na is different than Na plus 1. To give you an example in terms of physical properties, the element sodium is a very reactive metal, will burst into flames if exposed to water. But sodium cation is a common component of sodium salt, and you put it on your French fries. Okay, so this is the end of our chapter on sort of a basic introduction to the structure of atoms. In the next set of lectures, we'll do a deep dive into the electron configuration of atoms. See you then.